In this video, we're going to go back and look in a little bit more detail at physical changes and changes of state, and tying back in our discussion of intermolecular forces that we talked about a little while ago. Changes of state are, just as they imply, the process of going from one physical state to another. And so solid to a liquid, solid to a liquid, liquid to a gas, gas to a liquid, and so forth. Changes of state are physical changes because the covalent bonds, or ionic, but the bonds in general, the intramolecular forces, are not formed or broken in the process. We're not actually breaking up the chemical. Those bonds are staying intact. The intermolecular forces, however, the forces in between the molecules, those are affected. And it's important to note as we go on in this discussion and in our next lecture that intermolecular forces actually are not present in the gas phase. There's enough kinetic energy amongst the molecules in the gas phase to overcome any intermolecular forces that might exist between the molecules. Intermolecular forces absolutely do exist in the liquid phase, and they're even stronger and more abundant in the solid phase. That's what holds liquids and solids together. A change of state from, and some of this are very familiar terms, but a change of state from the solid to the liquid phase is just melting. The reverse of that is freezing, going from the liquid to the solid phase. Shouldn't be any new terminology there. Changes of state going from the liquid to the gas phase, called either vaporization or evaporation. The reverse is condensation, from the gas to the liquid phase. Something you may not be aware of, although you've probably seen it, especially, or you've seen it in action, especially if you've been in Maine for any length of time, is that we can actually go directly from solids to gases and directly from gases to solids. A solid going directly to the gas phase is called sublimation. You see that happen with dry ice. Solid CO2 gets its name, dry ice, because as a solid, it exists as what would look like just a regular ice block. But due to some of its properties and conditions and some factors sort of beyond the scope of our course, but due to lots of various factors, under normal atmospheric conditions, solid dry ice, solid CO2 is going to sublime directly to the gas phase. It's going to skip the liquid phase altogether. And so a normal ice cube, an ice cube made of water, set it on your desk, it's going to melt to the liquid phase, heat it up enough, it's then going to go to the gas phase. But it's going to go through that process, solid to liquid to gas. Dry ice doesn't do that, directly solid to gas. That's why it's called dry ice. Set a chunk down on your desk, it's not going to make a puddle. It's not going to form a liquid. It's going to go directly to the gas phase. The opposite can also happen. Deposition is when something will go directly from the gas phase to the solid phase. This is how the frost appears on our windshields. That's what I mean by when I say you've seen it if you've lived in Maine. There's a solid, sometimes seems like 6, 7, or 8 months out of the year that we have to scrape our windshields off in the morning. And that's deposition. The water in the atmosphere, it's in the gas phase, strikes the windshield, and immediately goes to the solid phase. And so it's not like, if you were to watch the process occur, it's not like it goes from the gas phase in the atmosphere, hits the windshield and becomes a liquid, and then freezes to become a solid. It just goes directly over into the solid phase, skips the liquid phase completely. And so there are certain conditions in which that can happen. Under most circumstances, though, we do go through all three phases when we're either heating up or cooling down. When something is melting or vaporizing or subliming, what happens is that the intermolecular forces become disrupted as the kinetic energy of the molecules increases. So if we have two different molecules that are held together here by their intermolecular forces, what happens is as we add more temperature, as we add more energy and heat, the energy of those molecules starts to speed up. As that happens, eventually there'll be enough energy to overcome those intermolecular forces. And so in the solid phase, those intermolecular forces are pretty much keeping things locked in. A little bit of vibrating, but the molecules are basically locked into each other. A little bit more energy and a little bit more condensation. Now the molecules still stick together, but they're able to slip and slide over each other a little bit. There's the liquid phase. Even more energy, and now the molecules can disrupt the intermolecular forces completely. There's the gas phase. During condensation and freezing, the exact same, condensation, freezing, and deposition, the exact opposite happens. We go from basically no intermolecular forces in the gas phase, just all bouncing around. We start to lose kinetic energy to a point where the molecules will then start to stick together a little bit due to the intermolecular forces. And so, and this stands to reason if we think about it, and it's something that you already intuitively know, energy must be added for melting, vaporization, and sublimation to occur, and energy must be removed for freezing, condensing, and deposition to occur. We also have something that we call evaporative cooling. Evaporative cooling is caused by the removal of heat from the surroundings during evaporation. Essentially, that's why we sweat. Water evaporates off of our skin, leaves us cooler. Just trying to see if there's anything more. And basically, I've already talked about everything else that is on this slide and give you my neat little hand demonstrations there. We can graph this. And so a heating curve shows the temperature change of a substance as we add energy. Temperature always increases linearly as we add energy. Temperature is going to increase, except during phase changes. During a phase change, when something is melting or when something is vaporizing, or the opposite, condensing or freezing, at those points, all of the energy being put into the system goes into disrupting our intermolecular forces. So the energy does not change while we are going through those phase changes. Sorry, the temperature does not change. The energy certainly does. So here's a good example here. So here we have water. Here we have water at, maybe negative 20 degrees C, something like that. Definitely well below the freezing point. So a solid block of ice. We're adding energy to it. We're adding heat, we're adding heat, we're adding heat. As we're doing that, our block of ice is warming up until we get to the melting point. Once we're at that point, now all of the energy is going into melting that ice. So we're going from 100% solid phase here to now 100% liquid phase. And during that time, the temperature does not change until we get to 100% liquid. At that point, now the temperature starts rising again as we continue to add heat until we get to, sure enough, the boiling point. Now all of the energy goes into going us from 100% liquid, 100% liquid to 100% gas. Now the temperature can rise again. So with that in mind, think about this. If you, for some reason, had to be burned by either 100% water at 100 degrees C or steam at 100 degrees C, same exact temperature, is one of them going to be worse? The answer is absolutely. That steam will burn you a heck of a lot more at the same temperature because you've added a lot more heat. That steam contains a lot more energy than what the liquid water does at the same temperature. And so I like to throw that example out there and have you look at this heating curve because it really demonstrates that heat and temperature are not the same thing. They're related to each other, but they're absolutely not the same. And actually, we don't need to get into our heats of fusion and heats of vaporization. Some of these slides I have in because sometimes I copy them over from another course, to be quite honest. But we're not going to get into those. I do want to point out, though, that if this curve was flipped, or if we go back the other way, it's just a cooling curve. We go from a gas at maybe 150 degrees C, cool it down until we get to the vaporization or condensation point. At this point, we're going to start to condense to a liquid until we get to all liquid. Then we cool it down even more, cool down, cool down, cool down until we get to the freezing point. Then we're going to freeze until we're at a solid, and then we can cool the solid down. We talked about that. The melting point and the boiling point of a substance are unique physical characteristics that can help us identify a substance. They're unique to particular substances. It's also important to note that the melting point of a substance is the exact same temperature as the freezing point. The temperature is identical. Water will melt. If it's a solid and you're raising the temperature, it will melt at 0 degrees C. If water is a liquid and you're lowering the temperature, it will freeze at 0 degrees C. Same with the boiling point. Liquid water, heat it up, it's going to boil at 100 degrees C. Water vapor, cool it down, it's going to condense at 100 degrees C. And so melting slash freezing point and boiling slash condensation point, exact same temperature, it just depends on what direction you're going. And so now let's talk about that role that intermolecular forces play. And so again, remembering that really when we're talking about melting something or vaporizing something, what we're talking about is that disruption of intermolecular forces. And so compounds that have weaker intermolecular forces do not need as much energy added to them in order to melt or to vaporize. And so compounds with weaker intermolecular forces will have lower melting points and lower boiling points. And so things like non-polar covalent compounds have very low melting points and very low boiling points because they have only very weak London dispersion forces existing in them. Compounds that have hydrogen bonding, however, much higher melting points and boiling points. Let's look at an example of that. So all of these compounds, well, butane and acetone anyway, same basic size, they have the same molecular mass. Butane only has London forces existing for intermolecular forces, has a boiling point of 30 degrees C. Acetone, now we have something with a dipole-dipole force in there. Its boiling point is almost twice of that in Celsius of butane. But then we have something like water, very, very small, only 18 grams per mole, very much smaller than either acetone or butane. But the hydrogen bonding means that the forces that hold it together are much, much, much stronger. And so that leads to a much higher boiling point and would also thus be much higher melting points for all of these. The shape and the size can also play a role in these physical properties. If we look at isobutane versus butane, they both have only London forces, and they both, in fact, have the same exact chemical formula. They're both C4H10 with identical molecular weights, but the shapes of these are going to play a big role. Isobutane, because of the sort of shape with a carbon in the middle and then other CH3s sort of hanging off the sides of it, is going to be shaped kind of like a ball. And so other isobutanes interacting with that, there's only a limited amount of surface area for those London forces to act on. Butane, however, is going to be much more like a flat sheet. Much more surface area now for the London forces to act on. That's going to increase that boiling point because there are stronger interactions holding it together. And then if we compare butane and octane, octane, much longer. And so we start to go from, something that might only be actually like my fingertips, maybe just with butane, to now octane, much longer chains, more area for the London forces to act on. That's going to raise our boiling point. And so we can do some comparisons there with everything else being equal. And so if you have only London forces that exist, and you look at sort of the shape is about the same between these two, sort of this sheet type shape, kind of flat, then you can look at these and say, well, yeah, octane's going to have a higher boiling point because it's longer. Or you could look at these two and say, well, they're the same size, same formula, but because of the shape of this one ending up in sort of more of that ball shape, going to have a lower boiling point than that of butane. There's another property of liquids called vapor pressure. Vapor pressure is actually, here we go. Diagram helps much more with vapor pressure than me talking about it. So if we have a container, let's say this container is sealed off and it has some liquid in here. And so this is just space. This is all just empty space in our container. Remember that that temperature is a measure of the average kinetic energy of molecules. And so when we're looking at the molecules that are making up this liquid here, maybe it's just water. So lots of molecules in here. There are going to be molecules near the surface that actually do have enough kinetic energy to escape into the gas phase. And so there'll always be some molecules that are up here in the gas phase. Some of those will have enough energy to drop back down into the liquid phase. And that sort of keeps happening back and forth until this equilibrium is reached, where there are some that have enough to get up to the gas phase, some that have enough to drop back down to the liquid phase. But the net result of that is that there's always, up in this space above the liquid level, there are always going to be some gas molecules up there. That causes a bit of pressure. That's vapor pressure. And so you might have experienced this if you've had perhaps maybe just a bottle of water, something without carbonation. Sometimes you open it up and there's still a little bit of a, you get that little bit of a gas escaping noise when you open it up, even though it's not carbonated. That's because some vapor pressure is built up in there. Some of those molecules that have made their way to the gas phase, there's a little bit of pressure behind that cap that's released when you open the cap. Which leads us to defining pressure. Pressure is a force per unit area that's exerted by gas particles that collide with the walls of their container. We'll be talking more about pressure in the next video, but just know that for now, that pressure is a force per unit area. A liquid is considered volatile if it has a high vapor pressure. If the molecules readily enter the gas phase, even at temperatures that are not approaching boiling. Something like gasoline. Gasoline's very volatile. And so that the fact that it's volatile just means that a sample of gasoline will easily enter into the gas phase even when the temperature is not approaching boiling point. Vapor pressure also increases with temperature, and that should just make sense. In our example here, once I start raising our temperature of the liquid, then more of these molecules are going to have enough energy to escape up into the gas phase, even though we're not at boiling yet. More molecules will have a chance to escape, and so we'll end up with more pressure up in that empty space. The actual formal definition of boiling point is the temperature at which the vapor pressure reaches 1. We're not going to worry too much about that, but that is the official definition. And actually, we'll be talking a little bit more about vapor pressure in the next video and pressure in general. So I'm not going to bother talking about this in this video, but we will talk about pressure in some more detail in our next video. And so that is it for now. Stay classy, USM.